Hi everyone, I am Onur Pusuluk from Koç University in Turkey. Thanks to the organizers of International Symposium on Correlated Electrons for giving me the chance to contribute this great conference by a recorded talk. Since the pioneering works of Heidler, London, Pauling, Slater, Mulliken, Hund, Hückel, and others at the interface of quantum chemistry and quantum physics, the principle of quantum superposition has been one of the most important theoretical and computational tools for understanding the nature of chemical bonds. For example, the approximations we use to describe chemical reality, such as hybridization, resonance, and molecular orbitals, are all in fact the superpositions of atomic orbitals. Similarly, the superpositions of different Slater determinants form the basic assumption behind the fastest and most accurate quantum chemistry methods that we have developed. Here, we focus on the next step in building our understanding of chemical phenomena using the tools of modern quantum information science. One of the most recent developments in this field is the discovery that superpositions shared in composite systems, namely quantum correlations, which are known as entanglement and more generally discord, can be used as a resource in quantum technologies. Quantum correlations are the characteristic traits of these new technologies that enforce their entire departure from quantum technologies 1.0. Quantum entanglement is considered to be the perfect example of quantum correlations, and its role as a resource in quantum technologies is well established. But discord can survive even in the dissipative environments that wash away all the entanglement. Also, it can serve a useful role as a resource in some tasks that are otherwise impossible, even in the absence of entanglement. Last but not least is the micro and nanoscale heat flow control in quantum thermodynamics. It has been both theoretically and experimentally demonstrated that quantum discord may lead to spontaneous heat flow from a cold body to a hot one. Also, as we showed very recently, discord can also prevent heat from flowing between two systems at different temperatures and actuate a heat exchange in the absence of any temperature difference without violating the second law of thermodynamics. These developments in the field of quantum information science are already reflected in the field of quantum chemistry by the emergence of the concept of orbital entanglement. However, until very recently, it has been incorrectly conceptualized in the literature as the total orbital correlations, which can be quantified by the measure called mutual information. This resulted in an overestimation of quantum correlations in molecular systems, since part of the mutual information is simply accounted for by the standard classical correlations. This paper is the first attempt to separate orbital-orbital correlations into classical and quantum parts. Here, the authors illustrated the effect of harmonic superselection rules on orbital correlations and provided an appropriate measure of orbital entanglement for the first time in the literature. However, this time, classical orbital correlations were associated by a distance-based measure, which quantifies both classical correlations and quantum discord. And this misconception is likely to cause the underestimate quantum orbital correlations. In this talk, we will introduce the notion of orbital discord, and this will enable us to focus on the next step in building our understanding of orbital correlations by presenting its first proper decomposition into classical and quantum parts. Our work builds on the recent developments in the harmonic information theory literature, and our methodology is compatible with all conventional quantum chemistry algorithms and softwares that allow one to print the coefficients of configurations. Assume that there are n sub e electrons and n molecular orbitals in a molecule. Using the occupation number representation, we first write the post-Hartree-Fock ground state in the 2n mod fermionic Fock space. Then we construct this following density matrix, but store only its non-zero elements for further calculations using this triplet sparse matrix representation. Next, we calculate single and two orbital reduced states by taking the partial trace of the state over the modes of remaining orbitals one by one. To this end, we exploited the inside-out fermionic partial trace operation proposed and investigated in these papers. As you notice, the qubit partial trace operation is modified for fermions by a phase factor here, which guarantees the consistent definition of local physical observables. Please check these references for details. Also, we investigated the effect of local superselection rules on fermionic mode correlations by taking the approach previously developed in these papers. We first measured the local parity or local particle number of the state before calculating orbital correlations. That is to say, we project the ground state density matrix, rho, here, into different sectors of the Fock space, as shown here. To illustrate this, let us consider these two orbital ground states. Local parity superselection rule eliminates these terms of the density matrix. After the application of particle number superselection rule, this term also vanishes. We investigate the pairwise orbital correlations by using two different definitions of quantum mutual information. The amount of the total correlations shared between any two molecular orbitals is measured by this well-known definition, where L and R denotes the left and right orbital in the pair, and S is the von Neumann entropy. We decompose the orbital correlations into its classical and quantum parts using the original definition of quantum discord, which can be found in these papers. Quantum generalization of an alternative definition of the mutual information is used to quantify the classical correlations, this C of R. Physically, it defines the amount of the maximum information about the left orbital that can be extracted after the measurements, performed on the right orbital. And this quantity is called as right classical correlations, since the measurements performed on the right orbital. Similarly, when the shared correlations between the orbitals are extracted by performing local measurements on the left orbital, one can end up with left classical correlation. We then quantify the quantum correlations between the orbitals L and R by the difference between these two different quantum generalizations of mutual information. Let us elaborate on the optimization used in the proper decomposition of the total correlations into classical and quantum parts. The number of parameters required in these optimization is greatly reduced in the presence of local superselection rules. For example, parity superselection rule only allows the measurements performed in this basis, whereas particle number superselection rule is conserved only if the measurements are carried out in this basis. The computational complexity of the optimization of two orbital discord under parity number superselection rule turns out to be the same as the one in 2-qubit calculation. Then, to check the separability of discordant orbital pairs, we exploit the fermionic partial transpose, which is proposed and investigated in these papers. Likewise, the fermionic partial trace, the most foundational distinction that separates the fermionic partial transpose from the qubit partial transpose, is again a phase factor, which can be calculated using these parameters. And this allows us to calculate the fermionic logarithmic negativity between the orbitals. Now, let's move on to our results. More accurate basis states are undoubtedly required to capture the orbital correlations more accurately. Here, you can see the orbital correlations in water molecule calculated using a correlation consistent basis set and a complete active space method. Here, we repeated our water calculations with a minimal basis set and a configuration interaction method with only the single and double excitations. The results between these two cases seem not to be very sensitive to side changes in the basis and the method. So let's continue with simpler calculations without any loss of generality. Here, the exact values of the total correlation I and entanglement E without superselection rule accompany their fractions remaining in the presence of superselection rules. Here, and similarly, here and here. P stands for the parity superselection rule, and N stands for the particle number superselection rule. Further, this table contains what percentage of the total correlation I decomposes into classical and quantum classical correlation and quantum discord in the presence of local parity superselection rule and local particle number superselection rule. Remarkably, we demonstrated that quantum orbital correlations can be stronger than classical orbital correlations, for example, between these pairs. Though this is not so often. The cases in question are the pairs including the fifth orbital, which is completely formed from the electron lone pair of the oxygen atom. Our results also reveal that quantum orbital correlations can survive even in the absence of orbital entanglement. Here, for example, and here again, and here once again. And it seems that this depends on the symmetries of the constituent orbitals. Here, this discordant orbital pairs 2, 7, 3, 6, and 4, 7. They are composed of occupied and vacant Hartree-Fock molecular orbitals that have opposite A sub 1 and B sub 2 symmetries. This finding suggests that the absence of orbital entanglement does not raise doubts about the usefulness of molecular systems as a resource in quantum technologies. Finally, we observe that orbital entanglement would be underestimated if the orbital density matrices were treated as qubit states. Here, Q stands for the qubit states. On the right, we calculate the entanglement in two orbital density matrices using a multipartite entanglement measure that becomes the negativity for two qubit states. Then it turns out that some density matrices, these green boxes, with fermionic mode entanglement are separable for qubit systems. For the proponyl molecule, the classical part of the total correlation is more dominant for all pairs of orbitals, as you can see here. But the quantum entanglement and discord possessed by the pairs of orbitals 11 and 11 and 20 and 20 and 13 are robust against local superselection rules, as you can see. These orbitals share a unique symmetry different from the rest. Actually, they display the pi orbital character. Also, under the local parity number superselection rule, here, close to 70 orbital pairs exhibiting quantum discord in the absence of entanglement. This observation supports the argument that the orbital entanglement cannot be regarded as an appropriate indicator of quantum orbital correlations. For the dicarbon anion, the orbitals 5, 6, and 7 do not share any quantum correlations with the other ones under local superselection rules. As a matter of fact, each of them is composed of alpha and beta modes having incompatible symmetries. For example, the orbital 5 actually is composed of this mode plus this mode, and the next orbitals are this pair and this pair, this mode and this mode, and this mode and this mode. Assume we redefine these three two-mode subsystems by combining the constituent alpha and beta modes with the same symmetry, which I mean that let's combine these two modes into a single orbital, these ones and these ones. In this case, the resulting orbitals become strongly correlated with the rest as shown here. Let's compare the previous picture. As a matter of fact, these new orbitals exist in the neutral dicarbon molecule. Then it is not clear which orbital definition would be more appropriate to understand what happens to the correlations in the transition from the neutral to the anionic state of the molecule. But the symmetry appears to be of importance. Actually, my research focuses on the interface of quantum information, quantum thermodynamics, quantum chemistry, and quantum biology. Since September 2020, I have been working as a principal investigator in a career development project entitled Resource Value of Biomolecular Correlations from the standpoint of quantum information and quantum thermodynamics. This is a 3-year-long project which is supported by the Scientific and Technological Research Council of Turkey, and it enables me to lead an independent and interdisciplinary junior research group at Koç University. We have local and global collaborators, each specialized in a different field as well. And today I try to summarize the first outcome of our project for you. More details can be found in this archive preprint, and I hope to share more works with you in the near future. Thank you for listening.